Good afternoon, good morning to everyone who's joined our webinar today. Thank you for taking the time out to join us. Next slide, please, Leandro. Yeah, welcome to the HEATS for Design, Automation and Optimization webinar. So today, between myself and Leandro, we'll kind of go through the different applications that are there for HEATS, what HEATS is used for, mainly from a design, automation and an optimization point of view, as well as going through a live demo of HEATS where we'll go through a static and a fatigue problem. We will integrate that within HEATS using SimCenter. And we will also then look at some results of an optimization problem. Just some housekeeping. So there are a few poll questions that we'll be running throughout the presentation just to get a feel for what the audience have been using, what they've been doing on specific applications. It would be good if you're able to take part in that poll because that will kind of help us tailor some of the content that we are showing in the presentation. Also to mention, we are happy to take questions. Please use the questions panel on the drop down in your WebEx session or webinar session and submit your questions. Both Leandro and I will be available at the end of the presentation. We'll go through any questions that have come in and we'll do our best to answer them. With that, I'd like to invite Leandro to introduce himself. Next slide, please, Leandro.
Hey. Yeah, thank you, Arjun. Thank you, Arjun. Welcome, everyone. It's a pleasure to be here to talk a little bit more about MDO, multidisciplinary optimization. My name is Leandro Garbin. I am based in Belgium, in Brussels, and I came from Brazil just about 8 months ago. I'm quite new over here in EMEA, and I took my master's degree on vehicle dynamics. I really do love vehicle dynamics. And over here in EMEA region, I'm responsible in terms of HEATS business development. I can cover the rural EMEA's region. And today, it's a really pleasure to join that webinar together with one of our biggest partner, Maya HTT. Thank you, Arjun.
Thanks, Leandro. Good afternoon, good morning, everyone. My name is Arjun Rajkumar, and I work for Maya HTT. I'm based in the UK, in London, but Maya HTT is a global partner. So we have offices in the US and in Canada, as well as the UK. So my background, I'm part of the pre-sales team. I have a master's degree in mechanical engineering design from the University of Manchester in the UK. I have 12 plus years of working on simulation and design exploration type problems. So I've done this for a few years now with a specific focus on process automation and design exploration. So with that, I'd like to spend about 30 seconds introducing Maya. So next slide, please, Leandro. So just talking a bit about Maya. So as Leandro kindly mentioned, so Maya are an award-winning partner for Siemens. We've been a partner for a long time, for 30 plus years, and we are involved in selling pretty much most of the simulation portfolio that Siemens have, in addition to other software as well. We've been a partner for more than 30 plus years. Maya hold a unique position in that we also develop some of the solutions or software modules on behalf of Siemens. So we author the solutions that power the Siemens, some of the Siemens solutions as well. And as you can see on this particular slide, we are present in a number of different domains. So it's not just the simulation aspect, which is going to be our focus today, but if there's some design problems or manufacturing applications that you are interested in, we can help you with those kind of applications, either through a services project or purely through software sales, but also automation and optimization, which as mentioned again, is again a topic that we're going to cover today. And with that, I'll let Leandro, next slide, please. We'll come to our first poll question. So I'm going to launch a poll. And hopefully this should take over your screens and you should be able to see a multiple choice option. So you can pick one which applies to your organization, and I'll give you about 30 seconds and then we can look at the results. And with that, I will bring the polling to a close and share the results. So just looking at the results here, so quite an interesting result, a mix of people here, Leandro. So there are about 22% of
Great.
the attendees haven't done any automation, but a significant number have attempted doing some automation, so post-processing scripts and stuff like that. So it shows there is a definite drive towards some kind of structure to help efficiency and those kind of things. And there's, yes, there are people who are using Heats and Eyesight and other tools as well. So a good mix of people in the audience. And with that, I guess you can start your section. Thanks for responding to the poll.
Yes. Oh, yes. Let's starting. So, uh, oops. Yes, over here. We will talk a lot during this section about innovation. So, ladies and gentlemen, innovate. Our company needs to innovate. Our company needs to innovate. But sometimes some companies doesn't know how to innovate and how to achieve their targets. What we are talking today, it's exactly about one technology that can help you to create the innovation and finding the new and even leverage your past good ideas. So with that, you can gain market share through innovative solutions. We will show some real examples over here, and even after my section, Arjun will run one technical demo, exactly what he told before. So over here is just one single example about how design space exploration can help you to create the innovation. Over here is just one optimization, one aero optimization, that with that single example, you can see that changing some parameters, that vehicle can have 8% of reduction of aerodynamics drag, a better traction, better stability, and much faster turnaround, and even can save money in terms of fuel economy. So that one is just one single example, changing some parameters and finding the new. You can leverage your better good ideas to bring innovation into your company. That kind of technology, we have no restrictions in terms of application. No restrictions. A lot of customers of ours came from automotive and transportation, aerospace and defense, marine, and even over here in Europe, in the Nordics, we have so many customers that work on the marine optimization. Really interesting application. Automotive and transportation, it's our biggest market. It's our biggest market, I can tell you. We have so many examples that even comes from electronics and semiconductors. So what we can understand and how the companies using CAE, using computational engineering, either the engineering, to simulate. Many of companies just use it just for the validate, troubleshoot, and prediction phase. What we are talking over here is to do much more. The idea is to find the new, looking for innovation. You can redefine your simulation strategy in terms to automate and even explore the new. Again, innovation, finding the innovation. With that technology, we can create the workflow and automatize. I will show you a little bit more later on. So that technology it's included in our STS portfolio. STS means simulation and testing solutions, that we have three main pillars: system simulation, CAE simulation, and physical tests. And that technology is a cross technology, exploration and analytics, and even data processing management. Over here in Europe, I am responsible for integrated solutions with two main technologies: Heats, that's exactly that we are talking today, and even Teamcenter simulation. So over here is just the all names, the all technology names that we have. And today we will talk about MDAO, multidisciplinary analysis and optimization, with the technology Heats and Heat Connect. I will show you that. So what is the idea about innovation? What's the idea about how you can find the new and even leverage your past good ideas. As soon you have your frozen design, so we are talking about in a validation phase, we can create their workflow and even automatize your workflow. As you can see later on, we have no restrictions in terms of integration even. We have no restrictions. We can integrate with the all CAD and all CAE tools. Again, please keep in mind, we can integrate with all CAE and all CAD tools. No restrictions. I will show you. We can work even on distributed execution. So you can run your single job in your own or in your own PC, in your own computer, or in a cloud, or in a cluster. And he can manage that job, can manage that process till you have a better design faster. This is exactly that means our slogan. So efficient search. Efficient search, it's our one of our main pillar that you can optimize and even finding the new. So a lot of people when we talk about heats, just thinking about optimization, but we can do much more than this. We can do much more than this. Optimization is just one single pillar that our main four. We have four main pillars, and our last pillar is insight and discovery. Our post processing, it's really powerful, really powerful. You can have the insights, and even when you join your own experience with that kind of technology, you can create innovation. You can go to the market much faster in terms to compete with your competitors. Over here, I will show you one technical example that comes from our customer Magna. It's a really important customers of us that on this single example, the challenge is to minimize the bumper mass, and even 20 geometry was available on that. The idea is to work in terms of combinations, but we have a lot of restrictions. Just to summarize, we need three main restrictions. The first restriction it is talk in terms of crash worthiness, the crash test. The second restrictions, the second constraint is the NVH targets. We need to achieve the NVH targets. And the third one is the fatigue behavior. So we are talking in terms of multi-domain optimization. This is exactly that we can run over here. And even one other example is we are talking about some different tools. So the CAD design comes from NX, the crash analysis, so the explicit analysis comes from LS-DYNA, and even we have Comet, as you can see in the slide before, just to work in terms of integration. So we can work with different kind of tools for different kinds of targets to optimize in one single job. Just on that example, we worked on process automation, distributed execution, efficient search, and insight and discovery. So our four main pillars that we are based. Just on that single example, we achieve 32% of mass reduction. We are talking about lightweight design. Lightweight design to covering uh, crash worthiness, so crash test, explicit analysis, NVH, target, and even fatigue behavior. Multi-domain optimization. And now I will ask my colleague Arjun to pull down over here our second question. Please, Arjun.
Just doing that. So that should appear on your screens now. So does your organization currently optimize your design workflow? So as before, I'll give about 30 to 45 seconds. Okay, with that,
Good
I'm
meets again.
closing the pre and let me just share the results so you can see for yourself. And I think there's some significant lean towards people having done some design exploration, Leandro. So that's good to see. Generally speaking, you get a bit more of an equal distribution, but it looks like 62% have done some design exploration as well as 24%. So a vast majority have used um, DOE and optimization techniques, which is good to know because I think that's what Leandro is going to talk about now. Yeah.
Excellent, excellent. I will show some difference between the traditional model and what we can offer. Great. So what we can understand in terms of traditional process for design space exploration? Sometimes, as soon you have your frozen design, you need to simplify your model. So you just need to remove some bolts, you need to remove some welds, select the algorithm. You don't know which kind of optimization strategy would you like to run. If it's genetic algorithm or if it's simulated annealing, you doesn't know. So you need to select. You need to tuning even your design optimization process. And just after that 3 phases, you starting to have some results. But what we can understand in terms of that traditional process, we have some problems on that. We really have some problems on that. Because if you simplify, we introduce some errors. If we select the algorithm, we require some interactions. And even if you need to tuning your process, you require some expertise. And what we can understand in terms of reactions, too error prone, too costly, and too difficult. You need to have a really smart people to work a master degree, a PhD, to work on that kind of application. And not sometimes you just not sometimes you opa pardon not sometimes you your design exploration you just use Sparkly is just used by expert, as I told you before, only for TOGAST optimization problems. So we just really delivered a limited innovation. What we can offer for you, what we can show you is HEATS, our modern process for design space exploration. Again, we challenge you to redefine your simulation strategy, your optimization strategy. You can redefine that process. Why? Because with HEATS, you don't need to simplify your model. So it's not necessary to include some errors over here. You don't need to select the algorithm. Why? Because we have just one algorithm. Our optimization algorithm called Sherpa. Sherpa is the name of our optimization algorithm, and you don't need to select the strategy because we have just one. Arjun, my colleague, will talk a little bit more about that in deep, about what is the difference between Sherpa and others optimization strategy. And even we don't need to tune the algorithm. It's not necessary because again, HEATS is absolutely one hybrid optimization algorithm, and he he can tune the optimization on the fly, absolutely on the fly and automatically. We can save a lot of time, of course, a lot of money as well, using that modern process for uh, design space exploration. Over here is just one video about the combination between HEATS and team center simulation. Why? Because we believe that the combination of that two tools could be a bridge for MBSE, Model-Based System Engineer. Please double check. So again, heats and Teamcenter simulation could be a bridge for your MBSE process. So we have no restrictions in terms of integration. Please keep in mind, we can integrate with all CAD and all CAE tools, no restrictions. And even we can include your own codes. We can help you to include your own code to run with heats. Here is just some other examples that came from US, from Trek. It's a really important customers of us. I know that so many people over here in Europe do love to ride a bike. The same for me, I really like to. And on that example, the idea is working with different tools. As you can see, CATIA V5 as a CAD, Abacus for stiffness weight, and Star CCM for the drag. Multidisciplinary optimization again. We need to cover the structural behavior and even the aerodynamics. So multidisciplinarity, multi-domain optimization. We have the challenges, of course, to minimize the aerodynamics drag, the frame mass, again, talking about lightweight design. We can include all kind of materials, no restrictions in terms of linearity, no linearity material, no problem about that. 21 geometric design variables, and as a result, we can have a combination about the best designs exactly to cover the targets. So that one is just another single example. For marine, as I told you in the beginning, it's a really important market for us. We have so many customers that comes from that area, even in UK, okay, even in UK, and we are absolutely available to provide more details about that kind of optimization, not just for the ship itself, but even for impellers, okay, for propellers, pardon. And the last one, the last example comes from plant simulation integration. So we have another portfolio over here at Siemens called MFE. And on that portfolio are included plant simulation for simulate your assembly line. And if you include heats in a strategy to optimize your assembly line, we can have a really good results, really good results. As you can see over here is just one assembly line. We have the targets to reduce the maximum material requirements, reduce the numbers of containers on the line, and even reduce the production time. Okay, this is the idea. And as you can see here on that single video, we have the baseline, as you can see here, with the output 1,500. We have the production time, the numbers of boxes, and even the empty sections. And as soon you optimize, we have no more empty sections. And even we decreased the time production. Again, it's another application, not just for research and development, for the product research and development, but even on the manufacturing area, we can apply heats. Some companies gain patents using heats. It's really important, even over here in Europe, in US, and in China, in Japan, pardon, we have some customers that gain patent using heats. Again, innovation is a key point for us. We are absolutely available to provide you a demonstration of heats. Okay, we have a really good synergy with Maya. Maya has a really good staff, technical staff, to provide you demonstration, training, and so on. Some testimonials, that kind of testimonials you can see in our official website, siemens.com/heats. And the roadmap for the optimization. Just to have an idea, we need one single day for heats training. And usually we offer the second day just to start to work with your own project. So the goal is very fast, very easy to use, and very intuitive to create the innovation in your company. And what we are launching the HEATS 2310, our new version. In our new version, we will include HEATS AI Accelerator, a lot of AI capabilities to you decrease the time of your analysis. You have a better design, even faster, even faster. On that new version, we will include the HEATS ROM Builder to order model reduction order model, so to reduce your model to run even faster in combination with AI. For example, I can send that slides for you. That slide's not confidential. That's that kind of slides deck. Heat Connect is our tool for web-based that you can share the results between your colleagues around the world. So it's a collaborative tool that you can see the results and even have some interactions during the optimization process. And Workflow Manager. Workflow Manager, we already have. We just increased the capabilities. And again, I really like to mention, we have no restrictions in terms of integration. We can integrate with the all CAD and all CAE tools. So over here in the chat, my colleague just will include the link for our official HEATS new release launch. Will be next week on October 25. You are all welcome to join us. Who will provide the presentation will be our product manager, exactly going deep about that subjects that I told you before. And now I just will ask my colleague again, Arjun. So please, Arjun, put over our third question to get the
Yes,
feedback from our audience.
yes, Leandro. So the third question should be up on screen now. So which of the following simulations do you perform? So as Leandro alluded to, HEATS is software or simulation agnostic. So pretty much anything that you would do, structures, CFD, durability or optimization, either parametric or non-parametric, HEATS has the ability to work with those kind of, or integrate and automate those simulation types as well.
Exactly.
Just give people a few more minutes. Okay, so I think we've got a reasonable number of responses. I'm going to close it and share the results. So pretty strong. So a majority are using structural analysis, again, tools like Simpson, Abacus, and Ansys. Significant numbers are using
Good.
CFD. So you did talk about a couple of CFD examples as well in your presentation, Leandro, so that's great.
Yes.
But 20% of the audience are looking at doing durability type analysis, as well as I would say 40% are looking at doing optimization, either parametric or non-parametric. There
Good.
are other analysis types I can see in the chat window in the question. So people are using NX Open for automation, which is great for extending the capabilities within Core NX. There's a kinematic dynamic simulation, or multi-body type simulations which somebody else is doing. So all of that is good. So I will let me close the poll, and
Excellent.
with that, let me share my screen. So I'm just going to change this over. So thanks, Leandro. So I will continue on from that point. Sorry, from current slide. So yes, so for the next stage, so we have a model that this is going to be a live technical demo of HEATS, as Leandro was alluding to. So it's a simple model of a spider bracket. So there are a few different steps involved in setting up the model. So we look at the setup of the model in detail. So we will spend some time understanding the FEA setup as well as the heats model setup. So we start off with an idealized part of the bracket. So this is based off of the master part and is controlled through geometric expression. So that's what we're going to be changing some dimensions on the specific bracket. We then go ahead and create a FEM file, which holds all the mesh and the material data, and the sim file, which has the static analysis and a fatigue run as well. So in terms of simulation, so we'll be running two simulations sequentially. So first we'll run a static analysis to understand what the stresses and strains are with appropriate boundary conditions on, and we'll follow that up with a fatigue analysis. Once we have the model ready, we're going to capture this workflow in heats, and initially we'll automate it and control the workflow through specific design variables. And once we have automated the workflow, we look at running an optimization problem. So just to give you a bit more clarity, so this is going to be our optimization statement. So we looked at the spider bracket itself. So our idea is it's a multi-objective optimization problem that we'll set up in the end. So we want to try and minimize the von Mises stresses, as well as, because we are running a fatigue analysis, we want to extend the life of this bracket. So we're going to try and minimize the maximum damage. I want to apply some constraints on the problem. So there is mean stress calculations which are done during the fatigue analysis. I want it to be above a certain value. And we are going to do that by modifying mainly geometry parameters in this particular example. So a number of different variables there: blend radius, the depth, and the pocket offsets, as well as the width offsets, as well as the tube outer diameter. So that's our problem statement. Just looking at the demo itself, so we'll split that up, or in the model setup, we'll split it up into like 4 segments. I'll spend about 5 minutes looking at explaining what the SimCenter model setup looks like. So review the mesh, the loads, the boundary conditions, etc., as well as the static and the fatigue analysis. Once that is done, I'll spend maybe a couple of minutes talking about the Heats GUI. For people who have not used Heats in the previously, it's a good opportunity for me to show you the nice and clean interface. It's quite it's quite user intuitive in terms of the interface, and just talk about the different tabs and the different capabilities there. Once we have done that, I will dive straight into the Heats model setup. So we will actually do the setup of this particular model. We will create the parameters. We'll set up the baseline run as well as the optimization run. And once that is done, we will spend some time looking at reviewing the results as well, the optimization results. So with that, I'm going to exit my screen and go into SimCenter. So we'll start by looking off at the SimCenter model setup. As I mentioned earlier, so it's a fairly straightforward part, which is the part file of the bracket. As you can see, so people who have used SimCenter before would know that there are a few different types of files that we need to take into account. It's simple geometry based off a sketch. So if we kind of go into the part navigator, you can see there's sketch parameters available which are being used to generate this particular geometry. But the key thing I want to show you is the fact that we have created, once the geometry has been built up, we have created some named expressions to control the different geometry parameters. So all the parameters that we saw in the optimization statement, those are available as variables for NX to change. We then go ahead and create an idealized part. So in SimCenter world, if you're working in a PLM or a controlled environment or a managed environment, we tend to recommend the creation of an idealized part, which is an associative copy of the master part. So we tend to do this for a number of reasons. So the master part could be locked by the designer, or this could open up possibilities for collaborative working. But if you do create an idealized part, you're not making changes to the master. You have the ability to kind of go back and use synchronous modeling capability to defeature the part further if you're interested in preparing the model for FEA analysis. Once you have the I part, we go away and build the FEM file. So the FEM file, as the name suggests, it is a finite element model file. So here, this is where we kind of go away and mesh the part, just to kind of show you all the type of mesh we have in this model. So it's a pretty standard mesh, second order TET elements. The element size is something that is, we can use the software as automatic estimation capabilities, but you can kind of go in and specify a finer mesh if you so wish to do so. We also use the mesh collectors to kind of assign the material property to the part itself. So in this particular case, we are using material data that the CAD part or the CAD designer created. So we're using inherited, but you can override that at the FEM level. The last step in the model creation for the fatigue and the FEA analysis is going to look at the simulation file. So there are, as I mentioned earlier, we are doing a couple of different simulations. So we're doing a basic simulation, which is a basic load simulation, solution 101, a linear static solution. Boundary conditions are pretty standard. So here we have these links on the spider that we have kind of fixed in space in the all degrees of freedom. We are also applying a load at the bottom end of the tube, and if you look at the load, it's basically 50 kilonewton pushing the bracket upwards in the negative z direction. So pretty simple and straightforward setup. So this model has been run, so we can have a look at the deformation, and you can look at how the model kind of deforms. As you can see, you have the deformation there, and you also have the von Mises stresses. So you can have, you're going to tend to have some spots of high stresses around the fillets where the legs kind of go and join the central tube. So that's the base analysis, that's the static analysis that we are going to run. Once the static analysis is run, we are going to use that to set up a strain life analysis or fatigue analysis. So this can be done quite easily by running a new solution process and picking Specialist Durability, which is built into the SimCenter interface. We've done that, so we've got our simple load solution. So if I quickly edit that, we are setting this up as a strain life analysis. The load definition is a simple duty cycle, and the duty cycle, I'll just go back and show you the duty cycle. So the duty cycle is essentially that block load on the structure, but we are repeating that for 2,500 repetitions. That's kind of specified here. So we have this going back to the solution. So it's a wizard-driven setup. So you can go strain life, stress life, and you have other options there as well. Load define and the material. So again, it's quite easy for us to go ahead and change the material, but we want to look at fatigue results for the material iron, cast iron, basically in this scenario. So this solution has also been run previously. So if we have a quick look at the results, we get some Specialist Durability plots in this scenario. So if you want to try and understand what the fatigue life is going to be for your structure, so that's something that we get. So this is this is better understood if we flip the contour plot. So obviously the higher the number, the better. So we'll just invert the spectrum, and we'll see, okay, so this is what it's going to look like. So pretty much most of the part has some really good fatigue life, 1 e to the power 37 cycles, but there are certain spots here which are only going to last about 13 duty cycles. So we clearly have a problem here that we want to try and optimize and solve. So that's the basic setup behind the underlying static analysis. So with that, I'm going to go to heats. So the second section. So here we're going to briefly talk about the heats. So as you can see, the heats interface that Leandro was mentioning is quite a clean, modular, and a modern interface. It's quite intuitive as well. We can have as many projects within a single session if you're so interested, but in this particular case, the key part here is to start building up the process. So this could be anything. So if you have multiple, so all the portals that Leandro was talking about are available. They ship with the library of heat, so you can kind of go in there and identify which components you want to bring in. So our case is more around if you're bringing in CAD from SolidWorks, if you're bringing in, you can kind of drag and drop that into the workflow. If you're then going to do some analysis using SimCenter 3D, that's fine. We drop it in the portal, and then finally, if you're doing some post processing with MATLAB, we can go ahead and do that as well. So again, if I just identify that, so MATLAB or Excel, maybe we can click that and we can apply that here. So we get rid of this analysis. So this window is mainly all about identifying the workflow and the sequence of execution of your solution of the study that you're trying to run. The next part is parameters. So here we build parameters. So we got to teach heats about the parameters. So we can kind of go away and create as many parameters as we want. So I'm going to show how you create multiple variables all at the same time. We can give these variables the names that we want to give them in terms of connecting up with the study that we have. Your variables can be continuous, can be discrete. You can have constant variables, or even we spoke about materials. So we could have something like, if you want to change the material, we can have that as a text variable as well, and tie it into the change of variable setup. Once you have, and again, you define variables and you define responses, so we can go ahead and add responses as well. Going to the tagging, is one of the most important parts. So it's the process of parsing the files to associate the variables that we've created in Heats with the right values and placeholders. So for most cases, I'm not going to do any tagging here at the minute, because I don't have any files that I'm pointing to. But it's the ability to associate the variables that we create in Heats with the right values in the underlying simulation. So for most cases or portals, this is fully automated. The user just has to pick the right value, as you will see in the demos shortly. We also have the auto tag functionality. The final step, and it is good to see, is the actual study. So we would always recommend that we start off with an evaluation only, like a baseline design, but you do have the ability to do full-blown parameter optimization, which I can see a majority of the people on the call have dabbled with in the past. If you want to do a DOE or a robustness or a reliability type analysis, we also have those kind of study types available out of the box. So that was a quick fire overview of the Heats GUI, and with that, I'm just going to go straight away into the model setup. So let me just close this project. We don't want to save it. I'm going to open up a new project and go to the process tab and get rid of the analysis. And the first thing that I'm going to do is identify the fact that it's a SimCenter 3D uh, uh, portal or an analysis that I'm going to integrate. So with that, I'm going to point to the sim file. So the model that I showed you with the results in that we have run as a template, we're going to kind of use that. So I'm going to right click, add input file. I'm going to point to the sim file and click open. This can take some time depending on how big the file is, and depending on other aspects. But basically what's happening in here is that Heats is kind of running SimCenter in the background. It is interrogating or parsing the sim file to look at what the model contains in terms of the parameters, the mesh, etc. And at the end of this process, what's it going to do? It's going to create all the dependent files, all the required files that are required for the analysis. It's going to do that automatically. So for the most part, us as end users, it just becomes a lot more easier. You could see while the parsing process is going on, you can see files appearing in the files tab. So here you have the input file name, which is at the bottom here, which is the SpiderSim3.sim that we are pointing to. You also have an automatically detected file, which is the output sim file, which has the results that we want to kind of parse in as well. So once this parsing operation completes, we will have access to the other tabs. So there's some warnings there, so it's not important for us to look at those warnings. We can ignore them safely. But as I was mentioning earlier, so you have the FEM file, which is automatically being created. All the files that we spoke about in the first um, in the SimCenter model, all of those files have been created. This is slightly different. One thing I want to mention is that we need to be careful about the version that we're using. So I built the model up in SimCenter 2212. So here in the preferences options, we have all the different analysis portals kind of selected. So here you can go to SimCenter 3D, and I've had to change that to make sure that the right version is kind of being pointed in. So once these files are done, remember we are running a fatigue analysis. So there's a couple of other files that I have to add manually. So this would be the fatigue. There's a small script which runs, which asks Heats to run the fatigue analysis after the static analysis is done. So I'm not going to tag that. I'm going to continue without auto tagging, and I'm also going to add. So what the fatigue analysis gives us is a comma separated value file with all the fatigue results. So I'm just going to add that as output. I'm not going to tag those either. So the next step for us is to go ahead and create the parameters. So as I showed you earlier, we can create parameters on the fly one by one, but what I'm going to do is I'm going to show you something else as a capability. I can import variables. So I already have variables listed in a CSV file. These are all the variables that we spoke about earlier with the minimum and the maximum values. So I can bring them in at the click of a button. I'm going to quickly create some responses. So I'm going to create a response for, we spoke about max von Mises. We spoke about the max damage. And we also spoke about the mean stress that we want to kind of include. So mean stress. So once this is done, the third step in the process is to go to the tagging. So here we'll go to the file itself. So this is the power of HEADS, is that it's quite user friendly and intuitive. So anything with a green arrow coming in is an input file. So I read that in. I'm going to go to the CAD expressions and go to the named expression. So this is HEADS is basically showing us all the parameters that are there in the underlying SimCenter file. So I'm just going to tag it. So blend radius matches with blend radius. I'm going to do the same for depth offset, pocket offset, tube outer dia, and width offset. So all of that is done. That's all the inputs done. I'm going to switch over to the output sim file to tag the output. So I go into solution, basic load, and I can look at the stresses, von Mises. I want the maximum or the absolute maximum, and I can tag that in as well. The mean stress and the damage parameters actually come from the CSV file from the fatigue analysis. So I also have the CSV file, as you noted, that I had mapped. I'm just going to toggle off these things to get a better view. So I'm just going to quickly identify what the max damage is, which sits there. We tag that. I'm also going to tag the mean stress, which if I scroll to the right, I find there's the mean stress value here, which I'm going to quickly tag. So with that, that's all the tagging done. So now it's completely set up to match those things. If I go to the study tab, I can go away and run a baseline. So our recommendation is always to run a evaluation only, which is a baseline study, just to check that the analysis runs. And once that is done, I'll show you the results for that. I'll also show you how we go away and create the optimization. Before that, I just have a quick slide to show you on Sherpa. And this can be quite important. So, it can be quite a barrier for people who have not done optimization in the past. Understanding or efficient search can be a barrier. So we can use this mountain climbing analogy to compare. And basically, when you're climbing a mountain, you don't necessarily know what the conditions are. Is it going to be icy, rocky? How's the walking path? Is it going to be heavy snow, and so on? And we don't want to be in a scenario where we rely on a single approach and we only have one set of equipment. What you potentially need in this is somebody like a Sherpa who has all of the strategies, who understands the equipment and tailors the approach to the terrain that is encountered. And these are the main advantages. Just to highlight some of those, the Sherpa multi-objective optimization is a hybrid adaptive. So it's hybrid because it can do both global and local searches simultaneously, or it can swap between the two quite easily. And it leverages the best of all the methods to try and get to a solution in a limited number of iterations. It is adaptive because it learns about the design space. So it's not going to just stick with a gradient-based approach or just get stuck in a local optimum. It's going to understand the design space. It's quite good, or it's extremely good with complex spaces. It can be quite good with simple spaces as well. So what it takes away is it takes away the barrier. It takes away all the variable screening, the space sampling, you doing a DOE to understand what the parameters are, then simplifying the model, maybe running a DOE to build approximation. So all of that complexity is kind of taken away in the first instance. So with that, so I wanted to show one slide on HEADS. I'll go back to the setup. So we'll go ahead and create a parameter optimization study. And here we are going to go for a Sherpa analysis or a Sherpa. It's the objectives I have aren't competing. So I'm trying to minimize the von Mises stress. I'm also trying to minimize the fatigue. So they are not competing. So we don't need a Pareto plot as such. So I'm just going to run maybe 100 evaluations. I'm going to pick all my variables which are going to be available. And in terms of responses, as I mentioned earlier, I want to minimize the von Mises stress. I want to minimize the damage. I want a constraint on the mean stress, and I want it to be I want it to at least have a value of 30 megapascal. And with this setup, I'm going to go to the run tab, and we can go away and hit the model to run. So what I've done in this scenario is I've actually run the analysis. So we have some results that we can review. This is what you get at the end of that particular analysis. So there are two things that we have run. So I'll just show you this. We've run a baseline run, which is a single run. We always recommend that you test it and make sure that the results are fine or the analysis actually runs. And with that, once that is comfortably done, we go to the optimization problem. So it's been set up exactly how we specified it in the demo before. So it's done 100 runs. It's taken about an hour and 43 minutes. So it's pretty quick. 58 were feasible, which is great. 31 were infeasible, which means that the designs were successful, but they didn't meet our constraints. That's fine as well. It shows that you're exploring the design space. 11 of the designs actually had errors, and what that means is the analysis failed because the geometry maybe didn't regenerate correctly. So that's one thing to keep in mind as a future study, is to try and ensure that your geometry can regenerate for the combination of parameters that you are specifying. But you can see Heats can handle that as well. It's not going to get stuck. It's going to carry on running the analysis. So study details, so we can kind of have a look at that. Best design is 75. I straight away typically go into the design details. So here you can actually see, and it's pretty neat because we've kind of set up to capture screenshots from the model. So you don't actually have to leave Heats to review the results. So you can look at the model. For each design, you can actually see that the dimension of the part changes. You can physically see things. Error designs won't have any images, but you can see things changing. You can change to mean stress if you want to look at the mean stress plots. If you want whatever plots you have created, we need to basically tell Heats that these are the plots to capture, and it will capture all of those plots for us. So you can do quite some early stage post processing within Heats before having to go to the SimCenter model and have a look at the results. In terms of additional post processing, so we have parallel data charts, which are brilliant. So very similar to a view that Leandro kind of showed earlier. This shows all the different input variables with your output, so you can kind of have a look at that. Sometimes this is not this might not be the best way to look at things, so we can change this from a radial to a spider plot as well. The design data is quite interesting. It gives you a tabular information about all the different variables and their values. It's a unique view which allows useful view to look into the model, sortable by designs and so on. You can go ahead and create correlation plot. So this is a plot showing max damage and max von Mises. As you can imagine, these are not competing objectives. They are kind of going down to the same um, zero, that they're going down to the same objective, so they go in the same direction. So you're not going to get a Pareto plot, but you do get a curve which goes to a single point, which will be your best design. It's also important, so we can quickly look at correlation plots. It helps us understand what our most important parameters are. So in this case, as we expect, so if you look at one of the outputs here, so let's say the max von Mises, and we look at the relation of max von Mises, if we scroll down to the tube diameter, you can see that has the highest value there of all the different parameters. So, and it has a negative sign associated with it, which means that increasing the tube diameter decreases your von Mises stresses and vice versa. So the correlation plot is also quite a strong tool for us to look at understanding what our key variables are. So with that, I'm just going to go to the last section, which is talking about the different advantages of Heat. So ease of use, it's very quick start, quite a user-friendly interface in terms of using the model. Accelerated designs, once you've automated stuff, you can very quickly start looking at different designs, areas which you haven't seen. So quite easy integration. So not just SimCenter, but also Leandro showed a number of examples with CATIA and other tools which it can seamlessly integrate with. And there's deeper insight. So we'll probably do another session on looking at just the post-processing tools, but there's a lot of significant capability there in that section as well. So just to summarize, the four key enabling technologies for Heats: process automation, which automates the data with out-of-the-box portals available. Distributed execution, leverage all of your IT resources, so you can run stuff on not just on your local machine, but also on distributed number clusters or on the cloud if you so wish to do so. Efficient search, use Sherpa. If you don't want to use Sherpa, we also have multiple other objectives, optimization algorithms available: gradient based, pattern searches, or genetic algorithms. You can use any of those. And insight and discovery, there's some significant, Leandro spoke about the AI capability that's coming through, but there's significant post-processing capabilities available. It's not just correlation plots, it's self-organizing maps, it's 3D graphs, it's trying to understand Pareto plots and so on. So there's a lot of information, a lot of decision support available right at the end. Um, keep learning. So again, the recording will be shared with you at the end. It takes a couple of days, but you'll be sent links to the recording. A lot of now examples available of heats being used with number of different tools, so 185 plus technical insights and deep dives on 21 different videos. These are all on the Siemens website. Things that we kind of put on social media as well, and also knowledge base articles.